Replacing a bridge is difficult. Replacing an airport is difficult. Replacing the entire power grid of a country with more than 1 billion people without ever switching it off shouldn't be possible at all. Yet engineers spent roughly a decade doing exactly that, rebuilding the backbone of a national electrical network while it never stopped delivering power, not for a single second, to a country that couldn't afford to lose it. Every stage of the project had to happen live, on a grid that was already running, already carrying the full weight of a nation's factories, hospitals, and homes. So how do you rebuild the largest power grid on Earth while it's still running? Chapter 1. The grid was built for a different country. The old grid wasn't broken. It simply couldn't support the country growing on top of it. In the early 2000s, rolling blackouts were hitting hundreds of millions of people across the eastern provinces, the same stretch of coastline where the country's biggest cities and factories sat. The power those cities needed didn't exist nearby. The coal reserves capable of generating it sat thousands of kilometers away, out in the west. The only way to move that energy east was to dig it out of the ground and load it onto trains. That solution created a bigger problem than the one it solved. By the middle of the decade, the sheer volume of coal moving across the country was clogging the national rail network so badly there was no room left for ordinary freight. Transporting the fuel was consuming an ever-growing share of the capacity meant to move everything else. Building more power plants near demand wasn't solving the imbalance. It was just moving the bottleneck from the power lines to the railway tracks instead. More trains weren't going to fix this. The only real fix was to stop moving the fuel entirely and start moving the electricity itself. Chapter 2. Moving electricity across a continent. If coal couldn't move fast enough by rail, the electricity would have to move instead directly across thousands of kilometers of desert, mountains, and seismic terrain no transmission network had ever crossed at this scale. Standard grids move power as alternating current because it's easy to step voltage up and down for local neighborhoods. But alternating current bleeds energy across long distances, the electrical equivalent of pushing a swing by constantly reversing direction. Direct current pushes in one direction only, like a steady hand on that same swing, and over 3,000 kilometers, that difference isn't small. It's the gap between losing about 5% of the power in transit and losing closer to 40. Direct current solved the distance problem. It created an entirely new one at both ends of the line. Converting alternating current into direct current and back again at the destination required converter stations of a complexity nobody had proven reliable at this voltage. Early prototype components failed under the heat load almost immediately. Engineers didn't retreat to safer, lower voltages. They pushed straight past the incremental steps every other grid in the world had taken, aiming directly for a voltage nobody had operated commercially before, betting the entire project on hardware that didn't exist yet. Inside the finished converter halls, the equipment involved looks less like a power station and more like something built to contain a controlled explosion. Valve modules are suspended from the ceiling on insulating rods, never touching the ground, because at over 1 million volts, contact with the earth would vaporize solid concrete on the spot. The air is filtered to a dust tolerance measured in a fraction of a percent, since a single stray particle near an active valve can trigger an arc violent enough to destroy the whole module. Thousands of gallons of cooling water circulate every minute just to keep the electronics from melting under their own load. Even solving the physics of the voltage itself wasn't going to be enough. This equipment had to survive running at that intensity every day, forever, without ever getting a break to cool down and be inspected properly. Chapter 3. Keeping the lights on. Here's the part that changes how this whole project should be understood. Building new transmission lines across empty desert was never really the hardest problem. The hardest problem was that none of it, not one line, not one converter station, could ever be fully switched off to fix a mistake. This wasn't a construction project happening beside a working grid. It was a live engineering operation performed directly on top of one, powering a nation that couldn't pause while the surgery was underway. The first long-distance corridor stretched over 1,400 kilometers and went live in the winter of 2009, running at a voltage no commercial line on Earth had operated at before. It worked right up until the season changed. Ice accumulation at high elevation did something to the conductors nobody had fully modeled because the insulators had been designed around the region's dry season, not its wet one. Engineers had proven the voltage could work. They still hadn't proven it could survive a full year. The fix couldn't wait for a shutdown that was never going to happen. Engineers had already built a backup pathway into the original design, an alternating current overlay network specifically there to reroute power the moment something in the new system failed, because the team going in had assumed failure was coming, even without knowing what form it would take. That redundancy, planned years before anyone knew exactly what would break, is what let repair crews fix a live, energized corridor without a single city downstream ever losing power while the work was underway. Chapter 4. Building a Smarter Grid. That backup pathway got tested again a decade later, and this time the failure was bigger. During a summer peak load period, the thermal models behind the converter stations turned out to have badly underestimated how much heat the equipment would generate under real demand. It was, by the project's own internal accounting, the single costliest miscalculation in the program's history, and it forced a retrofit across 4 operational stations simultaneously, none of which the grid could afford to lose for the months the fix would take. Redundancy had bought time. It hadn't solved the underlying problem. A grid this size couldn't keep surviving failures it discovered after the fact. It needed to see them coming instead. Digital monitoring systems went in across every major station and corridor, tracking temperature, load, and equipment condition in real time instead of waiting for a fault to announce itself. Automated dispatch systems began shifting power around developing problems before they became outages, deciding in seconds what used to take a human operator hours to diagnose. The grid stopped being something engineers simply built and started being something that had to watch itself continuously, because it could never be taken offline long enough to be checked by hand. Chapter 5. The Grid That Had to Power. The Future. None of this was only about fixing blackouts that had already happened. It was about a demand curve that was about to get dramatically steeper. Once electricity could move thousands of kilometers at an acceptable loss, the old logic reversed completely. Power plants no longer had to sit next to the cities that needed them. Coal in the west, hydropower in the southwest, wind farms across the north, all of it could now reach demand centers a continent away. Wind and solar projects that would have been stranded, generating power with nowhere to send it, suddenly became viable investments the moment the transmission existed to carry their output. The grid had been built to solve yesterday's blackouts. It was about to be asked to carry a demand curve nobody had designed it for yet. That mattered because the demand curve wasn't standing still either. Electric vehicles, high-speed rail, and increasingly automated factories were all pulling more power through the same grid that used to run considerably lighter loads. A network built to move coal-fired electricity from west to east became, without anyone redesigning its purpose from scratch, the same network capable of carrying a much larger renewable build-out to the same cities. People who hear this story usually picture new cables strung across the countryside. That's not really what happened. What actually got rebuilt was the logic of how electricity moves across one of the largest, most complex power systems ever operated, redesigned span by span, while it continued supplying a country that was never given the option to wait. Every converter station, every backup pathway, every monitoring system exists because the grid was never allowed, the one thing every other major infrastructure project eventually gets, a moment where it's acceptable to turn everything off and start over. The lines were never really the achievement. The achievement was proving that a system this size could be torn apart and rebuilt from underneath itself without the people relying on it ever noticing the difference. Most people never think about the power grid until it fails. The engineers behind this one spent a decade making sure it never had to, rebuilding the machine while it kept running, one live corridor at a time.